Okay, guys, so what we're going to be talking about in this lesson is momentum and conservation of momentum. So now that we've kind of looked at energy and seen that as a different perspective on motion, we're going to use this information now to talk about momentum. And specifically, we're going to use a similar trick, the way we did with energy, that made it really advantageous to use. That was conservation of energy. Well, today we're going to use that same principle with momentum to show another really neat trick that we can do with momentum. So we have momentum here. It's sort of like energy, but not the same, right? So pretty much if I have an object and it is moving, then it has momentum. Similar to when I had kinetic energy. So remember when I had kinetic energy, the conditions were that the object has mass and it's moving, right? So any object that has mass and is moving has some kinetic energy. Similarly, it also has momentum. But why are we going to introduce this just subtly different term than kinetic energy? I'm going to show you right now that we can do something really neat with this, right? So let's say I have two objects. I have this ball here, it's moving with some velocity, and here we have a box that has a much bigger mass, but it's not moving, okay? So what we're going to do is momentum will help us to figure out what is going to happen when these two things collide. Momentum is all about collisions and transferring momentum, right? So almost like transferring energy between two things. So will be the main use for this tool, momentum. So first, calculating momentum, it's very simple, mass times velocity, but remember that this velocity has direction. So if my ball is moving to the right here, my velocity would be positive, then my momentum would be positive. But similarly, if my ball was moving here to the left, then my momentum would be negative because my velocity would be negative, this would be negative, this whole thing would be negative, right? So keep that in mind, okay? That's the biggest thing that trips up my students when they're first being introduced to this topic. Okay, secondarily, let's kind of see here, even if you have a very large mass, if you are not moving, it doesn't have any momentum, okay? So I've sort of shown here momentum calculations for two objects. Now, one last thing before we move on is we're going to have this very important term, which is the sum of all of my momentum in my system, my total momentum, my net momentum, right? And that is just going to be adding up all the momentum of each object in your picture. Okay, so this is my picture right here. I have two objects. This has momentum, right? I mean, technically this has zero momentum, but they each have the capacity to have momentum. So if I wanted to find the total momentum of this system, of this image, I would just add up their momentums, each one, right? So I'll do mv1 plus big M v2, and this will be my total momentum, keeping in mind that this would be 0 because my v is 0. Okay, so moving on. This term is going to be really important because we're going to need to be able to add up all of our momentum values so that we can exploit conservation of momentum. So in a simple way, we can just say that things have momentum, and throughout a collision, doesn't matter which type of collision it is, whether two things stick together or whether they bounce apart or they bounce 5 times, whatever happens during a collision before and after, if we don't consider friction, again, friction of like, let's say this box on this surface, right? So there can be friction of these two things sticking together. We can account for that, but any external factors, if nothing else comes in and we don't consider friction, let's say from the ground or air friction, then my momentum doesn't change. That means whatever my total momentum was before the collision and my total momentum after the collision here, these two things need to be equal, very similar to my energy where I had something flying through the air and my total energy had to stay constant. Well, this one, throughout a collision, my energy doesn't necessarily stay constant, but my momentum does stay constant, which is really good. So let's kind of see this in action with an example. So in this example I've drawn here, I have three objects. Okay, 2 kilograms, 5 kilograms, 3 kilograms. This first object is moving to the right at 4 meters per second. This object here is not moving, this large guy in the middle. And then this object right here is moving to the left at 2 meters per second. So eventually we can see that these things will hit each other, but they haven't yet. So first of all, what we need to be able to do is we need to be able to calculate the momentum of each object. Okay, so that's simply mass times velocity, mass times velocity, mass times velocity, just keeping these terms together for each one. And if we added up all of those together, momentum 1, momentum 2, and momentum 3, then we can add up all of this together to get our total momentum. And I call this momentum initial. You can see here, sometimes I'll write this as a shorthand of P original and P final instead of writing all of this out. It's just a shorthand. Okay, so let's go ahead and try this out. So if we do this, I will have my mass of object 1, which was 2 kilograms, and its velocity, which was 4. And then my mass of object 2 was 5 kilograms, and its velocity was 0. And my mass of object 3 was 3 kilograms, and its velocity was -2, okay? So remember, the negative is very important. So when we add all of these up, remember that right here I have a 0, so 5 times 0, this is going to go away. So all I need here is 2 times 4, which will give me 8, and 3 times -2, which will give me -6. So I should have 8 minus 6, which should equal 2. And now's a good time to discuss that our units for momentum are kilogram meters per second. So strangely here, we don't have a unit nickname like newtons or momentums or anything like that. So we usually just write this as kilogram meters per second. Okay, so how do I use this now? This is my initial momentum. So this is right here. And I know that this has to be equal to my final momentum. So at some point in the future, these things will hit each other. And let's say these stick together. This is an inelastic collision. If they do this, they'll become one big object, right, with one mass. And they'll have one velocity together that they'll share. But which way is it going to move? How fast is it going to move? All of these things we need to figure out. What actually using momentum makes this very easy. Since there's only one object, it has one mass, and it has one velocity. All I need is what would this number be in order to figure this whole thing out, right? So thankfully, using this right here, this value comes in here, so this should be 2 kilogram meters per second, just like we solved for before. This is equal to my big mass, okay, times my final velocity. Well, this right here is just all three of my objects put together, so we could find this out pretty easily, right? We would just have to do object 1 plus object 2 plus object 3. These are the masses, 2 kilograms, 5 kilograms, 3 kilograms. So putting these together, we have 10, okay, 10 kilograms. And we can multiply this with my final velocity. So here I have 2 equals 10 times my final velocity. So if we divide both sides by 10, my final velocity is 1/5 or 0.2 meters per second. So that'll say that these things were all moving. Who knows what's going to happen before, when they all stick together, they'll move to the right at 0.2 meters per second. Very slowly, but they'll move to the right. Okay? So this is very useful for us. This is, though, inelastic collision. Remember, when everything sticks together. There's also another case when things bounce off of each other. Okay? Like this example right here. I have a ball and another ball. This ball is going to hit and they're going to bounce off of each other. Okay, this is elastic. This right here is elastic collision. But the same rules apply, that my total momentum before and after has to stay constant. This one is a little more complicated though, because unlike in inelastic when everything's stuck together, here everything's going to go separate. So I have two velocities. It makes it really difficult. But I have some shortcuts. So I have included shortcuts for you here, one for velocity 1 and the other one for velocity 2. So if we use these formulas, you can find for any elastic collision of two objects, okay, you can find their final velocities using these. So let's go ahead and use these right now. Okay, they look a little bit daunting because they're very long, but they're pretty easy to use. So velocity 1 final is going to be this times my velocity 1 initial plus this times my velocity 2 initial. Okay, so let's go and do this. So we have mass 1 minus mass 2. We're going to say that this right here is 1 and this right here is 2. Okay, so doing this in here, we have 1 minus 2 over 1 plus 2 times my initial velocity of 1. Okay, and then we're going to do plus 2 times mass 2 over 1 plus 2. Go and do this. And my initial velocity of 2 was 0. Okay, so when we do this, this is really nice right now. We can already see this is going to become 0, that term, right? So coming back in here for initial velocity of 2, let's do a similar thing here. We're going to have mass 2 minus mass 1 over 1 plus 2. And this is going to be initial velocity of 2, so this is going to go away. And plus 2 times mass 1 over mass 1 plus mass 2. Initial velocity of 1 is going to be 1, right? So this is pretty neat because this one right here is multiplied by 0, so this is going to be 0. So following up with what we have right here, we can see that velocity 1 final is just going to be this term, which is negative 1 over 3 times 2, right? So I'll go ahead and just put it here, negative 2 over 3. And here I have velocity 2 final. This should equal to 2 times 1, which is 2, okay, over 1 plus 2, which is 3. So this is going to be 2 over 3. So you can see that velocity 1, it's going to move to the left with negative 2 over 3, okay, after it hits. And this velocity right here is going to be 2 over 3. So we can find what their final velocities will be just using these formulas right here. But there's going to be one case that is very useful, and we're going to use this a lot. You'll see this, probably in your homework or exams, and that is the super shortcut. Okay, if M1 and M2 are the same, okay, if they are the same, we get to use this super shortcut, and I'll show you right now, and I'll write this, that if M1 is equal to M2, if they're the same, that means this M1 and M2, they're the same, so this whole thing is going to be 0. And this whole thing is going to be 0 because it's M2 minus M1. They're the same. And right here, this 2 times M2 is going to be the same as the denominator because M1 and M2 are the same. So 2 times M2 over 2 times M2, we're going to do this twice right here. So this part right here is going to be equal to 1. And this is going to be equal to 1. So pretty nice the way this shakes out. What you get is just this right here. So my final velocity of 1 was my initial velocity of 2, and my final velocity of 2 is my initial velocity of 1. So what is this saying in simple terms, right? Is that, let's say I have two of these objects and they're the same mass, and they're moving towards each other. This one has a velocity of 5 meters per second. This one has a velocity of negative 1 meter per second. So what happens to them afterwards is number one will move at negative 1 meter per second, because that is what this guy was doing. So he's taken over the role of mass 2, and mass 2 has taken over the role of mass 1, and so mass 2 now is going to be moving at 5 meters per second. They essentially switch places of what they were doing. They don't switch directions, so it's not 5 and negative 5, 1, negative 1 and plus 1. It's really they switch places, right? This was mass 1, I'm going to call this M1, and this is M2. This right here is M1, and this right here is mass 2. So they've just switched places of what they're doing, right? They've switched their roles. So you guys can use this super shortcut to kind of skip any math, which is really nice. It's really handy to do here.